Let's look at the introduction. So here we're going to introduce the basic structure of a modern control, commonly used optimization algorithms, and how to formulate an optimal control problem, commonly used performance indexes, and towards the end we're going to look at 2 examples. This picture shows the classical control configuration. The frequency domain analysis is commonly used. In this feedback control structure, we have mainly 3 components. The first one is a plant, which describes the dynamic behavior of the object that we're interested in. This feedback block describes how the sensing system works, and the compensator, which is also our control. And this control will take actions based on the difference between the reference input and the output of the system. Then it will generate the control signal to change how the plant works. The classical control theory only works for a single input, single output system. In modern control theory, we are concerned with the multiple input and multiple output system. Here the configuration is composed of mainly 2 blocks. One is the plant, and the other one is the controller. So the controller will take actions based on the reference input and also the state variables. Optimization can be classified into 2 categories, the static optimization and the dynamic optimization. Static optimization is concerned with controlling a plant under steady state condition. That is, the system variables are not changing with respect to time. On the other side, the dynamic optimization is concerned with problems where the system variables change with the time. This figure provides an overview of an optimization algorithm and their relationships. So under optimization, there are generally 2 types of approaches. One is a geometric approach, the other one is an algebraic approach. The algebraic approach can also be decomposed into 2 groups, the single interest and the multiple interest. The game theory is normally used to deal with a problem that has multiple inputs. And for single interest problems, it can also be decomposed into 2 branches. One is deterministic, the other one is stochastic. For deterministic problems, according to how many stages it has, it can also be decomposed into the single stage optimization and also multiple stage optimization. Dynamic programming is a multiple stage optimization method. Under single stage optimization, we have a calculus and a Lagrange multiplier method. And Lagrange multipliers deal with the optimization of problem with constraints. Along with those lines, we have linear and nonlinear programming, calculus of variation, and functional analysis. In this course, we're going to focus on the calculus of variation. The optimal control problem is formulated by using 3 elements. The first one is a mathematical description of a process to be controlled. It's generally described by the set of differential equations. Second is a performance index. It is used to describe the criteria that we care. The last element is boundary conditions, including the initial and final conditions, as well as physical constraints of the states and control variables. This page summarizes a common used performance index, including time, the performance index for fuel consumption, which is the integration from T0 to Tf, the absolute value of U. If you have a multiple control input, we can use the summation of Ri times Ui, the absolute value of Ui's. The performance index for energy consumption is U transpose times R times U, and here R matrix describes the weighting of the energy consumptions in different channels. And the fourth one is the performance index for terminal error, which is defined as the difference of the final state and the desired final state, xd, at time tf. The performance index for squared tracking error is defined as the integration from T0 to Tf, E transpose times Q times E, and here E is the error between the state x and a desired state of xd. A general form of a performance index can be written in this form, which is composed of the final state error, the tracking error, and also the energy consumption. The constraints are normally in two groups. The first group is about the constraints on the controls. U can be limited within a range of U minus to U plus, and the state variables has a limit of from x minus to x plus. Then an optimal control problem can be summarized as follows. We have a differential equation to describe the dynamics of a process. The performance index in this general form, with some constraints on the control variable ut and the state variable xt. So let's look at some examples about how to put a problem into a standard optimal control problem. So in this example, a DC motor speed control system is described by using these equations, where x1 is the speed of a motor and x2 is the current in the armature circuit, and the control ut is the voltage applied to an amplifier supplying the motor. Formulate a performance index and optimal control problem to keep the speed constant at a particular value. Let's first define the state variable x as x1 and x2. And here both x1 and x2, they are a function of a time t. The desired constant value is defined as xd. The performance index is to keep the speed at a constant. So we want to keep x1 to be x1d. So the performance index can be defined as follows. J that is equal to the integration from t0 to tf, from the initial time to the final time, the error transpose times q times error dt, where the error e is defined as a difference between x and the desired value xd. And since we don't care about x2, we don't care about the current, so q can be constant c, and the other weight is 0. And the optimal control problem can be written as follows. The system dynamics can be put into standard static space form, where A is a 2x2 matrix. The first two entities are coming from the first equation, which has on the right hand side it is the coefficient of 0 for x1 and 25 for x2. So we have 0, 25 here. And the second row have a negative 400, negative 200, and the matrix B is simply 0 and 400. Let's look at a second example. For a simplified model of an automobile suspension system given like this, x is a position, and ut is the input to the suspension, and m here is the mass of the suspension, and k is the spring constant. We're going to formulate the optimal control problem for minimize the control energy and the passenger comfort. The performance index is composed of two parts. The first part is the minimum energy consumption, which is the integration from T0 to Tf, and U transpose time R time U. So here, since the U is a scalar, so we can write it as R times U squared plus the passenger comfort. The passenger comfort requires position and velocity to be kept at a constant 0. Here we want x to be 0, so the smaller x, the better. So here x is the vector, and x1 is defined as a position, and x2 is the velocity. The dynamics of the system can be written as follows. X dot is equal to A times X plus B times U. And here X is a vector, where the A matrix is equal to, the first equation is about x1, the x dot is equal to x2, so we have 0 and a 1 here. And the second equation is about x2 dot. x2 dot is equal to x double dot. X double dot can be solved from this equation. X double dot is equal to negative k over m times x, negative k over m here, plus nothing about x dot, so we have 0 here. And a B matrix has a form of 0. There's nothing in the first equation, because the first equation tells us x1 dot is equal to x2. And in the second equation, we have B divided by m. It's better to write two equations out if you have a hard time to see the relationships. You can write this into two equations. x1 dot is equal to x2, and x2 dot is equal to negative k over m times x plus b over m times u.